doping transition metal atoms in graphene for atomic scale tailoring of electronic, magnetic, and quantum topological properties. This article was published in the journal Carbon in 2020. Quantum computing and quantum sensing represent an emerging field with potential to transform computing as we know it. Due to the unique properties of qubits, quantum computers have the potential to solve problems that are beyond the capabilities of classical computers, including solving complex optimization problems, simulating complex physical systems, and breaking cryptography. The underlying functionality of these systems stems from the emergence of quantum phenomenon, which are usually only elicited at very small length scales. The fabrication of device structures on these length scales is therefore highly desirable, the ultimate limit being atomically precise manufacturing. One approach to manipulating atomic structures is by using a focused electron beam in a scanning transmission electron microscope. With this approach, it has been shown that silicon atoms can be attached to a single layer of graphene and that they can be moved step by step through the graphene lattice. This was extended to the insertion of platinum atoms, and then to the insertion of chrome atoms. In this work, we show that this approach is generally applicable, and many different elements can be inserted into graphene this way. The basic strategy is to select a position where an impurity or dopant atom is desired, damage the lattice using the focused electron beam, and then sputter atoms from nearby nanoparticles, again using the e-beam, until an impurity atom attaches to the defect site. This process requires nearby nanoparticles from which to source the impurity atoms. To put these nanoparticles on the graphene surface, we use an e-beam evaporator. Here's an overview image of a sample with a small amount of nickel evaporated onto the surface. Because the evaporation process is very short, we don't get a continuous coating across the graphene, but instead we get nanoparticles. Between these nanoparticles, we can still find areas of clean graphene, and using the insertion technique described, we can put nickel atoms into the graphene lattice. In a similar fashion, we were able to also insert silicon, titanium, chrome, iron, cobalt, copper, palladium, silver, and platinum. These demonstrations suggest that this approach to atomic insertion in graphene is generally applicable. The question remains, however, which atomic structures and species are technologically relevant, interesting, or useful? To begin answering this question, we performed an extensive series of first-principle density functional theory calculations. A large swath of the periodic table was selected, and we investigated these elements as impurities at single and divacancy sites in the graphene. The calculations reveal the binding energies, electronic and magnetic properties, and band structures predicted for each configuration. From these results, we can start to make more informed decisions about what kinds of impurity atoms we should target. For example, if we are interested in creating a magnetic moment, manganese or iron might be appropriate choices. If we are interested in creating an electronic band gap, ruthenium or tin might be appropriate. If we are interested in topological insulators, we would look for Dirac bands where energy gaps open at the Dirac point upon application of spin-orbit coupling. Cases where this non-trivial band topology is present are highlighted in yellow, and the band structure for osmium is shown as an example. With this information, we can start to conceptualize the structural building blocks for topological electronic and spintronic applications. The experimental demonstrations indicate that such structures may be amenable to direct top-down fabrication in future device workflows. Links to the publication are provided in the comment section below.